This presentation is on colligative properties in colloids. So boiling point elevation is one of the colligative properties, and it's when you add a non-volatile solute to a solvent, the boiling point will go up. This is because you've lowered the vapor pressure. So since you have other particles in there, you have an attraction between those particles in the water. There's also less particles of water at the surface to evaporate. So these things work together to lower the vapor pressure of your solution. And once you lower the vapor pressure of your solution, that's going to cause your boiling point to get higher. It means you're going to need more energy now to create the vapor pressure necessary for your substance to be able to boil at that pressure. So your equations here, which is your change in your boiling point temperature equals your constant for boiling point times the molality of the particles in solution. So that K for your boiling point is different for each substance. So you'll have to look up what it is for each substance, or will be provided for you. And the more of the particles that you add to your solute, the higher you will raise the boiling point until you reach a saturation point, and then that's the max that you can have your boiling point increase. So examples of that is if you add a little salt to the water cooking your pasta, that does raise the boiling point of your solution a little bit, which will cook your pasta a little faster, but you'd have to actually add a huge quantity of salt before you'd see a noticeable difference. So really you're just doing that for flavor, but it will eventually work. Another example is antifreeze for the car engine. You add the antifreeze to the coolant and the water in the radiator of the car, and that then will raise the boiling point of the water. So on hot days, you're not going to be as likely to have your water boil out and build up too much pressure in your radiator and break your radiator. For freezing point depression, it's the same idea. Since you've lowered the vapor pressure, now your freezing point has gone down. You have a change in temperature for the freezing point, which is also going to have a constant for the freezing point. That constant for the freezing point is different than the constant for the boiling point, so make sure you're using the right number in your calculations. And again, times the molality of the particles that you have added. And just like with the boiling point, the more you add, the lower the freezing point will go, and this will continue to work until you reach the saturation point. So examples of that are salting the roads in the winter, where you're putting the salts on the ice or salting your sidewalk. That causes then the freezing point to go down, which means it has to be colder before your ice can form. We also use that process making ice cream because the cream does not freeze at 0 degrees Celsius. It has to be lower than that, so you have to add the salt around it. You don't add it to the ice cream, but you add it to the container around it, which then lowers the freezing point of the water around it, which then will freeze your ice cream. And then just like the antifreeze in a car helped with your boiling point increasing, having antifreeze in your radiator also helps your freezing point decrease, and that helps you in the winter, so that when it gets really cold outside, your water doesn't freeze in your radiator and make your cooling process for your engine inefficient. So the antifreeze then stays as a liquid, so it will continue to flow through your engine properly, and then it will keep your car engine from overheating in the winter. All right, so how does this work with the particles in solution? You have to recognize that it's different for ionic and molecular substances because the effect isn't based on what type of substance it is. It's based on how many moles of particles you're going to get in solution. So for glucose, even though it's C6H12O6, it doesn't break apart into particles that are individual ions or atoms when it goes into solution. So each glucose molecule counts as one particle. So if you have 1 mole of glucose in a kilogram of water, that's just 1 molal of particles. But if you look at sodium chloride, which we know is ionic and breaks up into 2 particles in water, it means that when it dissolves, you're going to get twice as many particles in solution. So 1 molal of sodium chloride is actually 2 molal of ions. And for calcium chloride, it would be 3 molal of ions, which is going to be much more advantageous, and that's why that's what we use for melting ice in the winter. So the effects are based on the number of particles you're going to get in solution. So for molecular substances or covalent substances, the number of moles of particles is the same as the number of moles of that substance you put in there. But for ionic compounds, you have to multiply it by how many ions you're going to get when it dissolves. So that's what the lowercase I value is in the equation. And that lowercase I is called the Van 't Hoff factor. And that is now looking at what your electrolyte or non-electrolyte number of particles is. So for sodium chloride, that value would be 2. For calcium chloride, that value for I would be 3. For glucose, that value is just going to be 1. And that's how you can see the difference very quickly using that Van 't Hoff factor. So when you look at what's really happening in solution, you have to understand that solutions aren't ideal. So the ideal Van 't Hoff factor for sodium chloride would be 2. But that doesn't mean that we're actually going to get 2 moles of particles in solution. Because as these particles float around in solution, they're going to find each other. And for some time, they're going to briefly stick together and make one particle. So this is going to lower that Van 't Hoff factor. You're not going to have to worry about this for calculations, but you should know that this is a thing that's out there, and it should make sense to you that this is happening. So if you look at sucrose, you realize that all the way across, no matter what your concentration of the solution is, your Van 't Hoff factor for sucrose is 1, because you're getting 1 particle of sucrose in there. They're not going to stick together effectively at all. For sodium chloride, though, you notice that the ideal value would be 2, because you would expect for each mole of sodium chloride to get 2 moles of particles. And when you have a concentration of 0.001 molal, you see that the Van 't Hoff factor is actually a little lower than 2. It's 1.97, because now you have those particles in there that are finding each other and sticking together, so you're not getting the full 2 particles per mole. As the concentration goes up and gets higher, you notice that that Van 't Hoff factor goes down, because the likelihood of those particles finding each other increases as concentration increases. So when you get to 0.1 molar, you see that the Van 't Hoff factor is only 1.87. You see that even more with the potassium sulfate, because your ideal value would be 3 for that, because you're going to get 3 ions in solution. But if you notice that when you get to 0.1 molal, you're getting only 2.32 particles in solution. So that's going to not have as much of an effect on the freezing point depression or the boiling point elevation. Magnesium sulfate, you can see, is actually really effective at finding itself and sticking together, which should make sense because they're -2 and +2 charged ions that are going to be very attracted to each other when they find each other in solution. And so you can see that the Van 't Hoff factor decreases rapidly as your concentration increases from 2 all the way down to 1.21 when you get to 0.1 molal. So you have to account for the fact that these solutions are not ideal when you do your real calculations. Again, this is not going to be something that you're really going to have to worry about, but it should make sense that these concentrations increasing is going to cause these ions to find each other and not act like a true perfect solution. All right, so let's talk about colloids. Again, neither of these topics are really important for your AP test, but they are important for your college level chemistry, which is why we're covering these things. So colloids are homogeneous mixtures of 2 or more substances which are not solutions. So the reason why they're not solutions is because these substances are present as larger particles than those found in the solution. So we classify it differently. We have a dispersing medium, the substance in a colloid found in the greater extent. So this would be the same as your solvent in your solution, but we're called a dispersing medium because it's a colloid. And your dispersed phase would be like your solute, but again, since it's a colloid, we give it a different name, and this is the substance found in the lesser extent. For solutions, the ions and molecules have a size of about 10 to the -7 centimeters. In colloids, we're talking about 10 to the -7 to 10 to the -5 centimeters. So these are going to be things like fat globules and proteins and things that are much larger than the ions and molecules that we would have in the solutions we've worked with in class. They're still too small to settle out of the solution due to gravity, so they still stay suspended. And you can see that when you think of milk and the fat globules floating around in milk and things like that. So it's not going to settle out, it's not going to separate, it's still homogeneous, but these particles are larger, so they behave differently. There are several types of colloids depending on the physical state of the dispersing medium and the dispersed phase. So this chart gives you all the different types of colloids that you could be dealing with and what they're called. So if you disperse a liquid in a gas, we call that a fog or an aerosol. If it's a solid in a gas, that's what smoke is. It's also called an aerosol. If we put a gas in a liquid, that's a foam, like whipped cream. If we put a liquid in a liquid, that's an emulsion, like milk or mayonnaise. If we put a solid in a liquid, we call that a sol. That would be paint, right? You have the plastic pieces floating around in the liquid. When the liquid evaporates, your paint dries into a solid, or ink is the same sort of thing. If you put a gas in a solid, we call that a solid foam. That's a marshmallow. If you put a liquid or a solid in a solid, those are called emulsions, like butter or pearls. Solid in a solid is kind of an odd one, but the rest should be things that you've experienced and make sense to you. So just so you know where these names come from. All right, so with the colloids being larger particles, it means that when light is going through it, the light will be scattered. And so we can actually see the light passing through the liquid phase. And that reflection of light, making it visible to us, lets us know that we're dealing with larger particles than ions or small molecules. So that's how we know it's a colloid. So we refer to that as the Tyndall effect, that when you shine a light through a solution. Sometimes you can even see that in your house. You have a beam of light coming, around a shade or something, and you could actually see the beam move across your room. That's because you have lots of things in the air. Maybe somebody just cooked breakfast, so you have some smoke in your room. There's some dust in your room. There's all sorts of things suspended in there that can cause that to happen. Maybe your humidity is really high because you have a humidifier in your room, so you actually can have things dissolved in the water droplets reflecting that to you. It's almost like having a cloud at that point. So that's what the Tyndall effect is. That won't happen with solutions. It will only happen with colloids. So there's an example of the Tyndall effect of the light being bounced and scattered by the colloidal particles that are in the solution. And that's why we get to see the light, because it reflects the light outward towards us. So we have colloids that can be broken up into two categories. Since these are now more complicated molecules, we refer to them as hydrophilic or hydrophobic. So most of the time we are dealing with colloids where water is the dispersing medium. And so what we're looking at with hydrophilic and hydrophobic is whether it loves water or hates water. And not surprisingly, that water loving and water hating is dependent upon the polarity of the substance. So molecules arrange themselves so that the hydrophobic portions are oriented towards each other. So if you have a giant molecule that has lots of water-hating parts to it, it's actually going to fold inward so that that non-polar part of the molecule is surrounding itself, and the polar part of the molecule is outside interacting with the water. And so the hydrophilic portions will be on the outside, the hydrophobic portions will be on the inside. So there's your example of some polar things that are outside, and then the more complicated non-polar part of the protein would be that blob in the middle. So it's still able to interact with the water, but most of it is folded inward. So this has a lot to do with how your proteins fold when they're floating around in your body, and your cellular structure and a lot of those things. Typical hydrophilic groups would be the ones you'd expect: carbon and oxygen, hydroxide or alcohol groups, NH groups, those things that are going to be very polar or charged. Hydrophobic colloids need to be stabilized in water by adding a surfactant so that you reduce the water surface tension, and that will allow the mixing to occur. So if you want to think about a good surfactant, that's what we call soaps. So you take these oils that are hydrophobic and you add your soap to it, and then that makes it able to interact with the water. So the way it works is we absorb these soap molecules to the surface of the colloid, and then that makes the colloid hydrophilic, and now it's stabilized in water. So if you have oil and water, it's going to separate, but you add sodium stearate, which is a type of soap. You'll see that commonly in the ingredients of a lot of soaps and shampoos. As you add that sodium stearate, it surrounds the oil in the water, and now you have the water able to interact with it. So it sticks to the outsides of it so that the oil droplets will repel each other, and now they interact with the water so that they can stay in solution. Right, so the reason why this works is because you have a long nonpolar tail or long hydrophobic tail and a small polar head, hydrophilic head, and those hydrophobic tails then stick to the oil droplet and leave the hydrophilic head on the surface, and that's what enables it to stabilize. So you end up with this giant structure where the sodium stearate completely surrounds the oil droplet and makes this it's called a micelle, but here you can see the shape of the sodium stearate, where you have that long nonpolar end of carbons and hydrogens and your polar end at the other side that's going to interact with the water. And so when you talk about dirt stains, they're all mostly oil-based, so the soaps are just like the sodium stearate that do this. Bile will do this, so that it can form an emulsion with fats in our intestines. Emulsifying agents that they add to foods help with this occurring. So this is all part of digestion. This is part of your moving of substances throughout the body, since water is our main way of moving materials through the body and through the cells. And this is how we can clean our oil-based stuff off of our clothing. All right, so this is what a micelle looks like. The pink would be your hydrophilic ends of your sodium stearate. The yellow would be, the pink would be your hydrophobic ends of the sodium stearate. The yellow would be your hydrophilic ends interacting with the water. And the blue in the middle is going to be your oil that is being held inside away from the water. And so this is the soap scum then that attaches to your sides of your shower that's really hard to get off, because they're these big giant molecules that have all sorts of mass and different polarities to it, and it makes it very, very difficult to get off. So all that soap scum is actually your nastiness mixed with soap. All right, so colloid particles are too small to be separated by physical means. They're still too small to filter, so you still have to do it the same way that you did it before. If you wanted to boil or evaporate, that still works. But since they're bigger, you can cause them to stick together, and it will take a shorter period of time before they will coagulate or get large enough that you can filter them out. So all you need is something that attracts all your colloidal particles together, and then you form that coagulation, which then is a particle that will be large enough to remove through filtration. All right, so the way you can cause things to coagulate would be heating it. So colloid particles move and are attracted to each other when they collide, so you're just increasing the probability of them finding each other. Or you can add an electrolyte, which will neutralize the surface charges on the colloidal particles. Dialysis uses this process to separate ions from the colloidal particles, and so we'll talk about dialysis in a little bit. But this is the one way that you can remove colloidal particles that's different from what you can do with solutions. A suspension now is when you get to the bigger particles. Now you're in a higher category of sizes than the solutions or colloids, and now these things are going to settle out due to gravity because of their size, but they move through the solution randomly because they're interacting with the smaller particles, and this zigzag pattern of them moving around is what we call Brownian motion. So the particles are larger than 10 to the minus 4 centimeters, which means now we can see these things under a microscope. So this would be like your clay, your silt, your sand, things like that now are going to be suspended. A lot of your medications are suspensions. The suspended particles will eventually settle out. So, if you have a muddy river, you go and take a bucket and scoop some of that water out. If you let the bucket sit for a while, eventually your solids fall to the bottom of the bucket and you have clean water on top. That's because all those solids are suspended particles. Faster water moves, the larger the particles it can suspend. All right, so the process of osmosis is the movement of a solid through a semi-permeable membrane from a dilute solution to a more concentrated one. So this is how stuff moves through cell walls, right? It only allows small particles, molecules, and ions to go through. So what you end up with is a pressure difference, and we call that osmotic pressure. And so you have a concentrated solution on one side and a dilute solution on the other. And your semi-permeable membrane doesn't allow the concentrated particles to move through it, but it does allow water to move through it. So since you have a less concentrated solution on the on the right, you expect that the water is going to be more likely to move through the membrane, because on the right side there's just simply more water molecules that are going to be bouncing off the membrane, because on the left side, since you have more stuff in the solution, there's a smaller concentration or a lower probability of water bouncing off the semi-permeable membrane. So as the water bounces off of it, it moves through, but there's much more moving to the left than there is to the right, because there's just simply more water molecules on the right. So what actually ends up happening is that you end up with more stuff on the left side. Your water actually travels through the membrane and forces the level higher on the left side and lower on the right side, and that difference is what we consider the osmotic pressure. So osmotic pressure is going to be related to that Van't Hoff factor and your molar concentration and your temperature in Kelvin and your gas law constant, and it's because your molarity is moles per liter, so it's just a modified form of the ideal gas law. Your number of moles of particles times your concentration times your gas constant times your temperature is what's going to give you your pressure. All right, when you talk about living cells, you have a couple conditions that can exist. When the concentration on the inside and outside of the cell is the same, we say it's isotonic, same concentration on both sides, in and out of the cell. If the concentration is greater on the inside, we call that a hypertonic cell, and that means the solution has a lower concentration, which is hypotonic solution. And the concentration is greater on the outside, then we're going to say we have a hypotonic cell because it's got less in it, and a hypertonic solution. So when we look at let's say, red blood cell, and obviously this is not to scale, red blood cell and plasma, when it has the same osmotic pressure, the red blood cell holds its size and everything's fine. But when you have situations where your concentrations of ions in your plasma changes, then you can have major damage happen to your red blood cells. For instance, in a hypertonic solution, the level of salt in the plasma is too high, so the water flows out of the cell and causes the cell to shrink, and we call that crenation. And that's very, very dangerous for you to have when, if this occurs, then you start to have major metabolic degradation occurring. Luckily, if you change this solution quickly and drink a lot of water, you can get this back. So this is one of the things that can happen with dehydration, where you've just taken way too much water out of your blood. In a hypotonic solution, where there's less in the solution, the cell then will begin to absorb the water because there's going to be more stuff inside. So the cell actually swells to the point that it ruptures, and this is called hemolysis. And this is actually the more dangerous of the two, because hemolysis means that you're going to have these parts of cells that are now permanently damaged floating through. So not only can you not fix this quickly, but also you have more of a likelihood of having clots form and things where you could get a stroke or a heart attack. So this would be, you've removed a lot of salts from your body, and you've replenished the water but not the salts. And that's the reason why you want to drink something like Gatorade when you've exercised heavily, to not just replenish the liquids, but also to replenish the electrolytes that you've lost, to prevent this from happening to your body. All right, so dialysis is the process where solvent and other small molecules can pass through a membrane. It's similar to osmosis, but the holes in the membrane are a little larger, so even some hydrated ions can pass through. So we have to do diffusion, osmosis, ultrafiltration. So this is basically how it works. The diffusion process is you have a high concentration of stuff inside the blood, because this is used on somebody who hasn't been able to filter the blood through the kidneys, right? The kidneys do the same sort of thing. So you are pulling the blood out of the body, you're running them into a machine where you have a semi-permeable membrane, and the person's blood has way too much stuff in it because it hasn't been emptied in a while. And so you have water with ions on the other side, and so the particles that are not in the fresh water on the other side of the membrane come out of the blood and cross through the semi-permeable membrane to get to the other side, and that's what lowers the concentration of those things in the body. And depending on the concentration of the electrolytes in the water solution that's outside of the body, they can control what electrolytes stay in the body so that the person doesn't have all the electrolytes removed and doesn't end up dying of that complication. The other process then is osmosis, where the person also has way too much water in their body because the kidneys aren't working, and so you have to get that water out. So they run it through another step where you have a semi-permeable membrane, and now the water provided by the equipment has sugar in it, but the sugar can't pass through the membrane. So the water that's in the body, in the plasma, goes through the membrane to equal the concentrations through osmosis, and that's how you get the excess water out of the body, by pumping that sugar water into the other side so that the water keeps going out and has that osmotic pressure to go through the membrane and balance it out. So these are all the things that you need to know about colligative properties and colloids. Thanks for listening.